start. Okay, now we're finally happy to have Gustavo Marques-Tavares from University of Maryland. Gustavo has done a lot of interesting work on the intersection between particle physics and cosmology, mostly, but also a lot of other interesting work. But he's going to tell us today about early universe cosmology from gravitational waves.
All right. Yeah, thank you very much for the nice introduction and for inviting me. I've given many talks at Davis, usually in person. It has always been a really fun place to visit. So I'm hoping that in the future I'll get to visit again in person and sort of catch up with everyone. But yeah, today I want to tell you a little bit about sort of recent work. So I guess this is all post the start of the COVID era work that I've been doing. The first work was with Anson Hook and David Araco, who is actually now somewhat local. He's in Stanford. And then some very recent work that I did with Anton and David Brzezinski, who is a very good graduate student here at UMD. And as Marcus was alluding, sort of, I've been very interested in thinking about how we can extract particle physics knowledge from cosmological data. And there's quite a lot that we can learn about fundamental physics, sort of about new particles and new interactions from cosmology. And in particular, sort of, we get very, very precise information about the universe now through the CMB, for example, when the temperature of the universe was around an electron volt. And, you know, we can really put very, very stringent constraints and maybe eventually discover something by doing, you know, detailed studies about the sort of these measurements that we can do, and which are dominated by physics that was happening around these temperatures of 1 EV. We can't really use the CMB to go much further into the past because of a combination that, you know, the fact that the photons enter thermal equilibrium erases a lot of information, and there's still information encoded in the fluctuations. But if you try to get information from earlier times, sort of nonlinearity spoil our ability to try to explore even earlier times. And there's a similar thing that we can also do by studying the matter power spectrum using its perturbations. And that allows us to go to slightly higher temperatures. But again, we can't really push much further because effectively we lose perturbativity of the system, and we don't really know how to make precise predictions. And lastly, sort of one of our first sort of detailed measurements in cosmology came from studying physics of temperatures around an MeV, which is sort of BBN, when the light nuclei started to be formed in cosmology. And again, here we had around the same time the decoupling of the neutrinos, and if we could directly see those neutrinos, we could now try to extract very detailed information about the universe at this much higher temperatures. And this is all very exciting. You know, there's lots of interesting things to do here. But really, I think the first thing that comes to mind when you think about cosmology as a laboratory for particle physics, that we really want to study even earlier eras when the temperature of the universe and the densities were much, much larger than anything we can try to accomplish in the lab today. That would really give us access to physics that we know we're very unlikely to be able to directly test in the laboratory. And as you've seen, sort of this combination of, you know, nonlinear growth of gravitation, of perturbations because of gravity, and thermalization both spoil our ability to try to go to much earlier time. So how could we try to sort of get a you know, detailed view of this window that is sort of, I think, very exciting from the particle physics perspective? And I think now there is hope. And the reason why there is hope is that we've now been able to start observing gravitational waves, which, you know, are just very, very special observable, because since gravitational waves almost by definition only interact gravitationally, the universe is essentially always transparent to gravitational waves. And so they can carry information from the earliest times, including from inflation, all the way to us. And in the way to us, they can encode information about what was happening to the universe as they were traversing on the way to us. And this is essentially what the talk will be about, is how sort of this propagation of gravitational waves to us can try to encode information about the early universe. And because we've just started really being able to measure gravitational waves, I think this is the right time to sort of spend some time thinking, how much can we learn from gravitational waves, and how can we interpret the data that we're going to get once we build even more powerful observatories? Okay, and this is essentially the theme of this talk. So here's a brief outline. I'll do a very brief introduction about sort of the gravitational waves and the stage that we're in now. And then I'll show how a combination of sort of essentially causality gives us some handle on what we expect for at least part of the spectrum of gravitational waves of cosmological origin. And because it will give us some control over what we expect from the spectrum, we can search for deviations of that spectrum that are coming from essentially new physics. So in particular, I'll explore how this sort of it will be very low frequencies, which are sort of, it will become clear, I think, as I explain. And the idea will be that the deviations from sort of the naive prediction in this low frequency spectrum can encode information about a modified expansion history of the universe, and also about the presence of free streaming particles in the very, very early universe. And then, so this was essentially what we did in the earlier paper, sort of understanding this effect. And then the last part of the talk will be about our more recent work, where we were doing essentially sort of a simple version of forecast of sensitivity of a few motivated BSM scenarios, assuming that, you know, some experiments that are being planned for the somewhat near future, sort of, especially LISA. Okay, and then I'll see that, you know, we can probe at least some parameter space for axions, and, you know, if we're lucky, we could also probe some parameter space for supersymmetry if it's out there. All right, so let me just begin. If you've forgotten or somehow slept through the last 7 years, or, you know, somehow your memory got affected because the last 2 years have been pretty tough. Since 2015, we've gained access to a different, essentially a different messenger in astronomy, which are gravitational waves. So in 2015, we detected the first direct measurement of gravitational waves in the LIGO Observatory, coming from the merger of two black holes. Since then, a new detector, Virgo, joined the collaboration, and together they've observed about 90 mergers of black holes and also neutron stars and combinations of those, although mostly black holes. And those are all transient signals in the sense that they're very, very short in time. You observe them by, I think the longest signal is about a second. So you just see this burst of, you know, activity in your detectors, and you look for the very detailed waveform, the phases of the wave, and etc. All carry detailed astrophysical information about those events. And we've already learned some astrophysics and hope to learn a lot more astrophysics from it. And there's even some proposals to try to do cosmological measurements using these transient events. But this is not what I'll talk about in this talk. So in this talk, I want to talk about the next target, which are stochastic gravitational wave signals. So something that is a lot more like the CMB, some signal that has been coming from all directions and is essentially constant in time. So we're not going to get any phase information, but so we're going to try to extract information from the power at different frequencies. And if we're very lucky, although this is not something I'll cover in this talk, we could also try to use anisotropies of that signal. But this is not something that I'll cover, although some of my colleagues here at UMD have spent time thinking about it. Here is a somewhat biased view of the experimental landscape. So those are mostly proposed experiments, and also LIGO in its final sensitivity, sort of when it reaches design sensitivity. And this is the sensitivity to stochastic gravitational wave signals as a function of frequency. And here, this omega is essentially the amount of power in gravitational waves in a given logarithmic frequency bin. Okay, so this is the type of thing that people like to use when they're talking about gravitational waves of cosmological origin. And you see that sort of with the new experiments, we're going to both cover a much wider range of frequencies, which translates to having sensitivity to things that were happening at different temperatures. And also they're going to be much more sensitive than LIGO if we really get to build those experiments. And in particular for our forecast analysis, we focused on LISA, which is sort of the most realistic near-term experiment that we're going to get. And then the SIGO, which is sort of the most, I think, optimistic detector that people are talking about nowadays. And of course, if we want to make any cosmological measurement using gravitational waves, and we want to get, you know, information from the universe as the gravitational waves are propagating to us, the gravitational waves need to be there in the first place. So we need some way to generate it. And here, you know, I admit that this is the trade-off that we're making. We're excited about gravitational waves because they interact so weakly with everyone. And so they can carry very detailed information about the early universe without thermalizing and losing information. But it also means that it's very hard to produce them. So we need to find special situations where we can actually produce gravitational waves. And there are a number of scenarios in which you produce gravitational waves through cosmology. The most obvious one is through inflation. So inflation itself, the same way that it generates the scalar density perturbations that we see on the CMB, it can also generate gravitational waves. And those we're searching for by looking for this B modes on the CMB. Those are usually very, at least in sort of simple inflation models, those are usually too small to be detected in this other detected directly. So we will see them indirectly through their effect on the CMB if we get to detect them. Then there's sort of, you can also get them if we get cosmic strings that could have been generated in the early universe through the breaking of some global or local symmetry in the early universe. And what I really want to focus on is the possibility that we get gravitational waves from first order phase transitions. Okay, so, and first order phase transitions are a relatively common dynamical effect that can arise when you have the breaking of gate symmetries in the early universe. So if there is, the universe goes from a temperature of symmetry preservation at high temperatures, for example, what happens to the Higgs, and at late times it goes to a symmetry breaking phase. In many theories, you would expect that phase transition that connects the two are first order, because you start out in the symmetry preserving vacuum and then you generate a symmetry breaking vacuum, and there's a separation between the two. So the transition happens through the nucleation of bubbles of the new vacuum, and as those bubbles expand and they collide, they generate very large anisotropic stresses that source a lot of gravitational waves. And there's a relatively generic prediction of many gauge theories, although not a guarantee in any particular gauge theory. And it will be important to us because not only they produce very strong signals, but also the fact that the time in which they're generating this gravitational wave is very short. It's less than an expansion time. And this is what will give us this handle of causality, because we'll know that things that are very widely separated and are uncorrelated, and that allows us to get an extra handle on the spectrum of those gravitational waves. And as I said, it's not a guarantee in any particular gauge theory, and we were somewhat unlucky in the standard model that if the standard model doesn't have any extra modification that we have not yet detected, the two opportunities that we had to generate gravitational waves from transitions in the standard model didn't get realized. And it's because the QCD phase transition would have been strongly first order had the strange quark been much lighter, sort of closer in mass to the up and down quark. And the electroweak phase transition would have been first order if the Higgs was lighter. That means sort of that the quartic was smaller. But this just didn't happen to be the case. So we'll have to assume that there's a BSM source that is generating these gravitational waves for us. And the rest of the talk, I want to say, what can we learn if such a source exists? And here's just an example signal. I don't want to sort of, I'm not advocating for any particular model. It's just I'm taking this from this nice paper here. And what I wanted to see is that sort of they have this essentially coming from a breaking of a B minus L symmetry, a baryon minus lepton number symmetry. And they're showing here the predicted signal by varying the parameters of the model. And the two things I want to emphasize here is one that, at least in this model, they get very strong gravitational waves, which would be, very easy to see in many of those experiments that are being proposed. But the other thing is that, as you see, the frequency dependence of the signal varies a lot based on small changes in the parameters of the model. So how can we try to do precision cosmology, given that things seem to depend so much on some yet to be known parameters of the BSM scenario that would generate the waves? And the reason lies again in this causality argument that I was telling you, which is that if you look at very low frequencies, which correspond to very long wavelength modes, in which are longer than the typical correlation lengths that you would encounter in this bubble nucleation, then the frequency, the shape of the frequency spectrum becomes universal, and we can actually understand this. And so by looking at deviations from this universal prediction is how we can try to measure new effects in cosmology. Okay, so now that this is what I wanted to say for introduction, and now I want to actually explain a little bit where that universal expectation for the frequency spectrum comes from. Okay, so, and please do interrupt me if you have any questions. So here, let's go, yeah, let me try to explain how, at least very, in some simplified way, how this expected universal scaling comes from. And the idea is that, you know, the gravitational waves are being sourced by anisotropic stress, so sort of, which are essentially sort of the off-diagonal pieces of the energy momentum tensor. So essentially quadruple moments and higher in the energy momentum tensor. And those are coming from the expansion and collision of these bubbles of new vacua, and also on the effect that they have in pushing the plasma of the universe around, that breaks homogeneity and very strongly and generates these large anisotropic stresses. But if you calculate the power of the stochastic signal in gravitational waves, it turns out that it is proportional to the 2-point function of the energy momentum of the anisotropic stress, which is this pi here. When I'm suppressing all kinds of, you know, Lorentz indices, since they're just going to make us more confused. So essentially, the signal will always be proportional to this 2-point function, where k is the Fourier transform of the spatial coordinates. Okay, and now if you think about how these bubbles those bubbles are generated by fluctuations. So they at the beginning, different bubbles are completely uncorrelated, and correlation can arise because as the bubbles are expanding, they can transmit signals over some distance. But that's because, this is why it's important now that the source is only effective. So you're only generating the gravitational waves through a very, very short period. So therefore, correlations will have a maximum size. So if I try to look at this 2-point function at wavelengths, sorry, yeah, at k at values of k, which are very, very small, which therefore correspond to very, very large distances, particular distances larger than the typical correlation length of the source, they are completely uncorrelated in spatial. If I'm doing this, the sort of the spatial correlators, which means that the Fourier component just becomes a constant. And this is just the fact that, you know, if you have something that any function that goes to 0 after some distance d, so the Fourier transform of that function has very, very small momenta, that Fourier transform goes to a constant. And so therefore, all of the lower momentum gravitational waves will see essentially the same source. And this is why you get the universal scaling, okay? Because the low wavelength modes are independent of the dynamics of the source. Is that clear? Sort of, I guess this is the main physics point that will allow us to actually make predictions.
So what's the typical scale you expect is cut off?
So it depends. So that depends a little bit on the details of the phase transition. But it will turn out that as far as we can, people have studied, and so this is something that we're still trying to understand exactly the robustness of this argument. All of the phase transitions, they essentially produce the signal in less than a Hubble time. And so we're essentially looking only at wavelengths that were larger than the horizon size when the phase transition happened. So that those are certainly uncorrelated because no signal could have traveled far enough to generate correlations at those lengths. We in principle can go to even shorter lengths. The typical length is the size of the bubbles when they started really percolating, sort of essentially when you concluded the phase transition has concluded. And that changes a little bit depending on how efficient the bubble nucleation rate is, or the parameter beta, if you've looked at phase transition literature. But we essentially will only really require, for most of our analysis, we'll look at wavelengths that are larger than the horizon size at the phase transition time. And as far as we understand the dynamics of this should be safe. Okay, so why is the dynamics of this long wavelength mode so simple? And we can understand it by making, you know, a fairly simple analysis. If I suppress all kinds of Lorentz indices, this is the equation for a gravitational wave mode, a Fourier component of the gravitational wave mode. And here, because the frequency that I'm interested in is going to be very, very small compared to the time scale of the phase transition, I'm also modeling the phase transition as essentially being instantaneous in time. And then you can relax this, but it just makes your life much easier to do the simplification. And if you solve this system for very short, only for a very, very short time period, so essentially just a time step after the phase transition, so that you're just outside of the support of the delta function, you find that the initial conditions that you have right after the phase transition completed is that the amplitude of the gravitational waves is still 0, but you gave it a little bit of a kick. So it's very much like when you have a piano and you hit a note, and then the hammer has just hammered the string, but the string has not had any time to actually move. So it's very much like the similar dynamics. But here it does depend on whether your wavelength is big or small compared to the horizon size, and it's essentially the question of whether your harmonic oscillator, which is being represented here by the gravitational wave, if it's underdamped or overdamped. And so for things that are small compared to the horizon size, then they get an amplitude that's dependent on their wavelength. While for things that are super horizon, they get an amplitude that's completely independent of their wavelength. So you see that the super horizon modes will really be very, very independent of most of the details of what happened in the phase transition, except for some overall amplitude that's going to be common to all of them at small k, and then the Hubble at the phase transition. But after production, very quickly, that this initial condition that I had here, that you only had kinetic, you've only excited the kinetic energy but no displacement, it very quickly gets shifted from kinetic energy directly to amplitude for the super horizon modes, which are overdamped. So you give it a kick, it moves a little bit as far as friction allows it, and then it gets stuck there. And it remains stuck up until the wavelength becomes of order the size of the horizon. At that point, it's allowed to start evolving again. And at that point, it starts oscillating like you would expect from a harmonic oscillator, and with an amplitude that's decaying proportional to the expansion factor A. So the amplitude is always decaying at the same rate. But as you see, this fact that it only starts really having interesting dynamics once it enters the horizon, once its wavelength is small enough that it fits inside the horizon, means that different wavelength modes will have different amounts of amplitude decay. Okay, so this is just encoded in this equation. So the amplitude is effectively sensitive to how long a mode spent inside versus outside the horizon. And this is giving you sensitivity to the expansion history of the universe, because this fact that you distinguish between being big or small compared to the horizon size is essentially telling, and it's sensitive to how long you spent in each of those two phases, gives you sensitivity essentially to how fast the universe was expanding at early times. And in particular, if you just have a sort of the expected radiation dominated universe, which is what we expect from just extrapolating to high energies, then we know how this conformal Hubble, I mean, this again, I'm sorry, I didn't emphasize, but this curly H is conformal Hubble, which is, Hubble with respect to conformal time. It scales as 1/A, and then we can just massage this expression, and we see that the amplitude is just given by this expression here, which is also the same for the modes that were inside the horizon. So in radiation domination, there's this coincidence that the dynamics is quite different from modes that started already inside the horizon versus modes that started outside the horizon. But once you've gone through the whole math, you end up getting essentially the same answer. And then you can compute from that the power, this sort of beam power, like per frequency power in gravitational waves, and you get this k-cubed behavior, which is sort of what people expect at low frequencies for gravitational waves. And there's some term that comes from phase space, some term that comes from the fact that the energy is proportional to the frequency squared. But then this last term here is not universal. It was very special from radiation domination. And if you had any other kind of equation of state for the universe, you would expect a different expression to show up here. And therefore, you would not expect this k-cubed behavior. So therefore, measuring deviations from this k cubed or f cubed, since the k and f are related, gives you a way to try to measure, deviations from radiation domination at very, very early stages of the universe. In particular, you can actually, if you assume, that for sufficiently long times, the equation of state was a constant, but you allow for a general equation of state, which is just encoded here by W, you get that you can just go through the same math, and then you find that the power in gravitational waves is given by this, somewhat ugly expression here. And if the gravitational, if the equation of state is sort of softer than radiation, then you get more power at low frequencies than you would naively expect. And if it's harder, something kind of like kination or maybe some other kind of weird equation of state in the early universe, then you'd suppress power at very low frequency modes. So, so this was one way in which we can test, some information that we currently have no access to from the early universe, is by measuring this deviation from this lobe of gravitational waves at very low frequencies. Another thing that can change this expected behavior, this universal scaling, is the presence of free streaming particles. So far we've assumed that after the phase transition ends, there's no more anisotropic stress in the universe, because anisotropic stress has decayed away, and therefore nothing can really nothing can source or absorb the gravitational waves as it's propagating to us, and therefore it's only the geometry, sort of the space-time itself, that's changing how that frequency would change. But it's not actually exactly true if you have free streaming particles in the early universe, because free streaming particles, the only thing that they do is that they keep following their geodesics. So therefore, if a gravitational wave passes through them, then that will change the geodesics, and it will change the trajectories. So even if you start out with completely homogeneous bath of free streaming particles, once a gravitational wave passes through, the change in their geodesics will induce an anisotropic stress, or it will induce essentially quadrupole moments for this free streaming particles, and that can change and effectively dampen some of the gravitational waves. And this was first realized, or at least first, more carefully studied by Weinberg. I don't actually know if someone had realized this earlier. And in the context of inflationary gravitational waves. So he was interested, knowing about what would happen to gravitational waves from inflation. And he realized that the fact that neutrinos decouple at temperatures of around an MeV would impact the low frequency gravitational waves. But in particular for his effect, because it was being generated at inflation, the free streaming particles were not there when the waves were generated. So they're only affecting the gravitational waves at very, very late times. And effectively what he found and he showed is that the only effect of this free streaming particles were for modes that were about to enter the horizon. So it was during this horizon crossing that you actually got any effect. And in particular, all of them saw essentially exactly the same effect. All gravitational waves from inflation got dampened, but they get dampened by the same amount. And when I say all of them, I mean only the frequencies that were outside the horizon when the neutrinos decoupled. Okay, but how do we understand it? We can actually compute, at least sort of in some perturbative way, what is the effect of the free streaming particles, and we can write the anisotropic stress that's being generated by this free streaming particles in terms of this integral that's proportional to the gravitational waves, the derivative of the gravitational waves of a given frequency, and times some kernel here. And an interesting thing to see is exactly the form of this kernel, which I'm not writing down. It's some Bessel function. But for the inflationary case, as I said, the gravitational waves were already given some amplitude, and this amplitude is frozen until very, very late times. So H prime is 0 up until almost the time that they entered the horizon. So that's why nothing is happening at very early times, except about the time when you start entering the horizon, then H prime starts being non-zero, and that's when K tau is about order 1. This is around this time here in this sort of kernel function. And then the kernel actually goes to 0 very, very quickly after that. So most of the dynamics is being dominated right around the time when K times conformal time is equal to 1. And that's why all gravitational waves essentially end up seeing the same thing because the effect is only there at a very, very specific time, and nothing else really depends on K. So it only depends on this product here. So it leads to this universal suppression that I discussed. However, for exactly the thing that I just discussed, the phase transition, we are in a very, very different regime. We're in a regime that right after the phase transition, there's no amplitude, and all of the energy is in the kinetic motion of the gravitational wave. So therefore, you can see that the effect of free streaming particles is going to be much, much larger in this case. And then this is something people had never realized. So in particular, for the very early stages, when, you know, the modes are still very, very super, yes.
Oh, sorry. Can I just wanted to understand this comparison. So what are the free streaming particles in inflation? Is it just that you're assuming that during inflation, there are some other particles? Can you just say, I'm just not clear, what are these free streaming particles?
Good. Yeah, no, I was a little, I think I was a little bit confusing when I said, so what Weinberg did, he assumed regular inflation. So there were no particles during inflation, effectively. But then at late times, when the gravitational waves are propagating to us after reheating, at some point the universe has free streaming particles, and then those free streaming particles can influence the propagation of those waves to us. And in particular, for the very, very low, for the low frequency modes of the gravitational waves generated during inflation, he showed that modes that were super horizon, when the neutrinos decoupled, that the neutrinos were the free streaming particle that he was interested in. So modes that enter the horizon after the temperatures dropped below an MeV gets this extra suppression. So that's the effect.
Yeah. Okay.
And because he showed that, you know, as long as there were no, I mean, maybe there's some interesting thing to be thought if there are light particles during inflation, although, you know, light particles during inflation are a little bit tricky because everything has Hubble mass. So I'm not exactly sure how to think, but there could be some effect there. I don't know if people have thought about it. I presume they haven't, just based on, you know, the fact that no one had thought about the effect for phase transition. But what he showed is as long as there was nothing during inflation, then the only effect arose from when the modes were about to enter the horizon. And it's because, you know, you really care that the H prime, the derivative of the gravitational wave amplitude is non-zero. And it's only non-negligible, this effect, when the gravitational waves were about to enter the horizon.
Okay, I got it.
Okay.
And now, and then can you repeat again why your case is different? I'm sorry, I'm making you repeat.
Yeah, no, that's good. Yeah, so for us, you know, because we had the fact that for the low frequency modes, the effect of the phase transition was so sudden that in the very beginning, right after the phase transition ends, that there's no amplitude displacement, and everything that then the phase transition does is it generates a non-zero derivative for the gravitational wave. So it gives it a little momentum. But a little momentum is exactly what sources this anisotropic stress. So therefore, the effect for phase transition seemed to be maximal in terms of the effect of free streaming particles.
So you sort of want free streaming particles that are there sort of right after the phase transition.
Or during, or during the phase transition.
Okay, got it.
Yeah, okay.
Thank you.
So for us, you know, and as you'll see, the most interesting effect is the thing that's happening right after the phase transition. So if it's right after the phase transition and the modes are super horizon, I can assume that k tau is very small compared to 1. So this is the condition that you're super very big compared to the horizon. And if you're in this regime, then the function is essentially a constant, right? So this kernel function here is a constant, and then you can just massage this integral, because then it's just an integral of h prime. So this is just proportional to the amplitude of so it's no longer an integral equation. It's just linear in the amplitude of the gravitational wave. So if I plug that in to the equation of motion of the gravitational wave mode, it's just effectively a time-dependent frequency term that shows up in that equation. And it's in particular, it's proportional to, I mean, here in this notation, it's proportional to tau. It's not super clear, but it's essentially, it's a mass term that's proportional to Hubble squared. So it's constant compared to, you know, so the difference between the new frequency and the Hubble and the Hubble friction is constant over time. And so this effect, even if it's, even if this frequency is small compared to Hubble, its ratio to Hubble remains constant. So it can cause an effect over very long periods of time, and it can cause superhorizon evolution in particular. And this is effectively what we see. So we can solve there are two ways that we can do things. We can either, use the simplified version where we assume that the effect is dominated by this early time, and then use this approximation, which is clearly not capturing the horizon entry physics. It's only capturing what's happening right after the phase transition. Or we can solve, the integral differential equation that we get from plugging that into the equations of motion. So the solving things numerically are all of the dots that we have here, and this is the ratio of the gravitational wave amplitude with amount of free streaming particles that's given by FFS. So this is the fraction of the energy density that is in free streaming radiation, compared to the case where you have no free streaming radiation. The same amount of radiation, but everything is interacting. So we're just comparing this ratio to isolate our effect. And you see that in fact, it does create a frequency dependent change in the spectrum, and that, there is some small difference between solving things exactly through doing numerical methods versus the solid line, which is what we get by ignoring horizon entry and just pretending that the term was just that mass term that we included. And as you see, if you make the fraction of free streaming particles very, very large, you even start imprinting some oscillatory pattern in the gravitational waves. And this is because if the free streaming particles is sufficiently large, this mass term that you're giving to the gravitational waves at early times is large enough that you can do full oscillations before the mode re-enters the horizon. Right. So as I was saying here, right? You have this. This rho of Fs over rho total is essentially that fraction that I was talking about. If this fraction is large enough, this can be order 1 compared to Hubble, and then you have time to do full oscillation, and therefore you imprint this oscillatory picture here. And we can actually understand what's happening, especially if the fraction is small. If the fraction is small, then you just get this power-dependent decrease in the spectrum, which is with an exponent that is dependent on the fraction of free streaming species. And for very, very large free streaming species, then you get this more complicated formula that has this oscillatory pattern. Like this, it's oscillatory in the log of the frequencies. So it's interesting, but it requires a lot of energy in free streaming species. So this is the summary of the effects that sort of we found, and that I want to explore in the second part of the talk, which are we're sensitive to the equation of state, particular deviations from f cubed that are proportional to variations in W compared to W equal to 1/3, which is what you would expect for the very early universe. So if we measure the gravitational waves very, very well at low frequencies, we can try to measure this deviation. And then free streaming species also cause a change in the spectrum, and it also sort of changed the slope, but proportional to the fraction of free streaming species. And it's actually hard to distinguish if you have if the effect is coming from the change of the equation of state or of the free streaming species. But luckily, there is a little bit of a bias that almost all models that we can think of would have W smaller than 1/3, like either equal to 1/3 or smaller, which means that this power that shows up here is positive, is negative. So it's 3 plus a positive number. So it makes the sorry, this is wrong. This is supposed to be a plus sign. Sorry. Yeah. So yeah, this here is supposed to be a plus sign. So this number here is positive, and so it's 3 minus a positive number. So it's decreasing less fast than k cubed, and so you get more power at low frequencies. And if you have free streaming species and you have the correct sign here, which I messed up, yeah, you get that it decreases faster as you go to lower frequencies. Therefore, you see less power. You see a steeper slope at low frequencies than k cubed. So these are the two effects that we're going to look after and make projections for future experiments. Okay, so this brings me to the last part of the talk, is which we still don't know. Well, we don't have the experiments. we don't know exactly what the source will look like, so we have to make projections based on some optimistic assumptions of what the source will look like, and hoping that the experiments are not going to find some extra noises that they're not expecting now. So there's a caveat to a lot of what I'm saying, but what I think is the right time to think, if we're optimistic about what those experiments can do, what can we hope to measure, assuming things are going to work as well as they're telling us. And of the obvious BSM target, I think, is sort of free streaming particles. We know we have many reasons to expect almost any theory beyond the standard model that has sufficiently large couplings that we could ever hope to, even in the asymptotic future, measure them in the laboratory. Those couplings are large enough that they would have thermalized at some point in the early universe. And if this is true, that it predicts some minimum amount of energy that went into this BSM sector that is yet undetected. And this is usually parameterized by this N effective, which is essentially comparing the energy density of the new particles to neutrinos, and then saying that cosmological experiments would infer that we're more than 3 neutrinos, essentially. And here is and so if you assume that things were in equilibrium with the standard model at sufficiently large temperatures, you can calculate what is the contribution to an effective if you know the particle content of the model that you're putting in, because it will depend on the number of degrees of freedom, essentially, right? So, and depending on when it decouples, so the x-axis here is the decoupling temperature, and depending on when it decoupled, the contribution to an effective is bigger or larger. Sorry, bigger or smaller, and it's because if it decouples very, very early, then it was a very small fraction of the energy density of the universe, and the rest of the energy density of the universe, as particles are going out of equilibrium, they keep heating up the photons, and so the relative energy between this initial particle that decoupled very early and the photons that ratio starts becoming smaller and smaller. So therefore, the contribution to an effective becomes smaller and smaller, and the current limit is about 20% or so on an effective, like 0.2 is roughly what we can get with current CMB experiments. And future CMB experiments are going to, and that tells us, that if we had even spin 1 or spin 1/2 particles, or 2 degrees of freedom, that's still very far away from what we could see. I think that course 0.2 corresponds to about 7 or 8 degrees of freedom in the early universe. That's if you're decoupling above the temperature, above the mass of the Higgs, essentially. Then future CMB stage 4 experiments, the line depends a little bit. I mean, I've seen it change a little bit over time, but it's still borderline if we could see, spin 1 or spin 1/2 particles of 2 degrees of freedom, and we would definitely not see a single degree of freedom, which is, for example, what you would expect with something like the axion or any kind of simple real or pseudo-scalar field. And so being able to measure, do better than the CMB would be great. But even being able to do as well as the CMB, it would be measuring particles at a different temperature of the universe, which we don't have any reason to expect that there was non-trivial evolution between when we measure things at the CMB and at the very early universe. So it would be really giving us complementary information. And of course, what I just told you is that with gravitational waves, we could definitely try to measure free streaming particles. So I think that's a very, very strong target, and I'll show the results for that. But there are some cases where when the phase transition happens, maybe the particles were still interacting, but we would still very much want to learn about those particles. So how well can we do if we're just trying to measure the effect of interacting particles that have sufficiently strong interactions with us, that they remain in equilibrium through fairly late stages of the universe. And the answer is that we can still do it, but it's harder. And the reason is that even when the universe was radiation dominated at very early times, the claim that the equation of state is exactly 1/3 is actually, it's an approximation. It's not the full story. And it's because, and we know that, because we know about the conformal anomaly. So if the equation of state was exactly 1/3, we know that the trace of the energy momentum tensor would be exactly 0. What we know in particular, because we have the standard model is described by quantum field theory, we know we can calculate this trace, and we know it's proportional to the beta functions in the standard model. And so therefore, there are corrections to this expectation that are proportional to the beta function. And in particular, you can go on and calculate a bunch of, vacuum diagrams at two loops in thermal field theory, and they will give you the right answer. And you get deviations from delta W that are going as this complicated combination here, which this is only including the gauge couplings and the Y top and the quartic, which are the non-negligible couplings of the standard model. And we see that the standard model itself predicts something that we should be able to measure. So there's a standard model prediction that we could go try to measure, which is that there's a deviation from W equal to 1/3, which is about 3 times 10 to the minus 4. So if we have very, very, very high precision in our measurement of gravitational waves, we could even see the effects of the conformal anomaly. And of course, if you have any new set of particles, either if they interact with any of the gauge couplings of the standard model, then they would change the beta function. So therefore, they would change this prediction. So we know we could try to see something from that. But even but delta W is actually something that depends on T to the 4th divided by rho, and rho is something that is linearly proportional to the number of degrees of freedom in the early universe. So even if something is coupled to us with a coupling that is a little bit too small to matter for any beta function, the change in G star, which enters this formula here, would be enough also to change this prediction. So it's not that we need something that has QCD or weak interactions. Anything that has sufficiently large couplings to be coupled to the plasma, which only requires couplings of order 10 to the minus 3, 10 to the minus 4, would be enough for us to see. So new particles. What is the sensitivity? Just sort of in the ballpark, so you get some feeling of what are the numbers we're talking about. For free streaming particles, we get sensitivities that are about a factor of % times the number of degrees of freedom which are in this free streaming species. So this is the kind of precision that we would need, the sort of % level precision on measuring that slope of that spectrum. While if we want to see either the conformal anomaly or any new particle that is changing things through, but that is interacting with the bath, then we need to see some things of the order of 10 to the minus 4 to 10 to the minus 5, depending on exactly how many degrees of freedom are there in the new sector. Okay, so first let's think one of the great examples, because it populates both scenarios, both interacting and non-interacting, are axions. So in here, I'll just be very, I'll not be very precise. I'll just talk about ALPS. So I'll only focus on this particular coupling here, the coupling to photons, and not care very much about the mass, assuming that it was sufficiently relativistic at high temperatures, or temperatures above the weak scale. And there's a boundary sort of, assuming this is the temperature of the phase transition, and this is this coupling GA gamma gamma. And if you are above this line, it means that at the time of the phase transition, the coupling was sufficiently strong that you were still coupled to the bath. And so therefore, in that case, you would really need to measure things to 10 to the minus 5 level. While if you are below this, then you only need to measure it to about 10 to the minus 2. Of course, there's some complicated transitioning here that we didn't really try to describe, how to measure something that's leaving equilibrium of the standard model. So this is something that we're interested in thinking about now. Okay, so this is essentially so if you're on the green region here, you only need to get % level precision, which I think is optimistic, but not too optimistic. I think if we have a sufficiently strong first order phase transition, as I'll show you, we can probably get here. Getting here will really require both luck in the source being extremely strong, and also that the experimentalists that are measuring these things are extremely careful and can really mitigate all kinds of foreground. And here's if you're a supersymmetry aficionado, how much would we need in order to measure the Mssm compared to the standard model? So here's the predictions for the standard model versus the Mssm as a function of the temperature. This is just the deviation from the equation of state coming from the conformal anomaly. So you see again that you would need to be able to measure the equation of state to a part in 10 to the 4, roughly, to be able to distinguish the standard model from the Mssm. So which I think is a great motivation to try to really push this program to the highest precision possible. Okay, so now I'm my last few minutes. I just want to show, can we actually reach those sensitivities, right? Okay, which I guess is the important question. Otherwise, this is there's some interesting math maybe. And in order to do this, again, I said we'll have to be somewhat optimistic because we haven't built those experiments yet and we haven't seen the signal. So, you know, there's a lot that we don't still understand about how the measurement is actually going to be. But I think in this condition, the right approach is to be, you know, cautiously optimistic. So we'll assume only instrumental noise, you know, which is something that the experimentalists, they're planning the experiment, they can give you. This is the expected instrumental noise. So this is what we're going to take. There's one extra thing that we, because we don't really know it super well, but you know, is a worry about the community that wants to do cosmology with gravitational waves, which is there are potential foreground coming from astrophysical sources that we cannot resolve and therefore also look stochastic in nature. And I think a lot of our ability to measure things will depend strongly on our ability to, you know, disentangle cosmological and astrophysical sources. And it's a very open area of research. So here we're going to ignore it because it's really something that people don't fully know yet, how well we'll be able to take this into account. And then we'll use this Fisher information matrix to determine optimal sensitivity. So the Fisher information matrix is essentially telling you, under some set of assumptions, what is the optimal sensitivity that you can achieve to a given signal. And you know, usually you can try to achieve this, although it's not always possible. And it is also not always the optimal. There's some, if this is the best way that you can get if you're doing some sort of unbiased estimator. So there's some ways in which you can do a little bit better, but I don't think it really matters for this kind of analysis. And so it's some complicated integral over frequencies. What really matters is theta here is parameterizing the parameter that we want to measure. So let's say the slope of the spectrum, right? The deviation from k cubed. And omega is the signal, the thing that the power spectrum of gravitational waves at a given frequency. And omega noise is the power spectrum of noise. So as you see, if the signal is sufficiently large, such that, you know, it's larger than the noise, then the noise essentially, the noise effectively cancels out, and you only depend on the gravitational wave. Like you essentially can ignore the noise. And at that point, what really matters is how high of a frequency you can probe and what is the maximum observation time. So this is the most optimistic take, is when, you know, your signal is sufficiently large that it's above the noise curve. And it's possible with you know, if you have a loud enough phase transition. And there are, we also need to have a template, a theoretical template for the power spectrum of the gravitational waves, and we are going to use phase transitions, and there's lots of modeling that goes on in doing this. We only really care about the amplitude, right? Because we're assuming that this low frequency tail is model independent. There are three contributions, you know, and I think the least understood one is turbulence. And in many models, sound waves are expected to be the dominant source. So the biggest part of the signal is going to come from sound waves, which are, you know, effects on the plasma coming from the expansion of the bubble. And there people have done simulations and have found this approximate formula for the power spectrum that I'm showing here. And you see there are two parameters, essentially alpha, which is characterizing how much of the energy, essentially is how much latent heat is released by the phase transition compared to the energy density of the universe at the time of the phase transition. So essentially sort of the typical, like a very strong phase transition will have alpha order 1, like about 1. And then beta is how quickly the phase transition is happening. And then that tells you sort of how big the bubbles get before they percolate, essentially. And you see the bigger alpha is, the stronger the signal is. And you see, you know, for large alpha, you even get things that are above the noise curve of Lisa. And then there's also dependence on the phase transition temperature. The larger phase transition temperature, the higher the frequency, the peak frequency of your signal is, right? So here's the sensitivity. Again, will depend on the phase transition. If we take alpha equal to 1, you know, it's a very strong phase transition. This is the kind of sensitivity we expect to get with Lisa, right? So you see for beta equal to 3, which is, you know, is very optimistic, I must say. LISA could even get, to the standard model value of the conformal anomaly. But for beta equal to 10 or higher, which is more realistic, we couldn't quite get there, but we could get percent level measurements over a wide range of phase transition temperatures. For the CIGO, which is a more futuristic experiment, there even for beta of 10, we could easily get into the standard model parameter space. We can even measure, the conformal anomaly for the standard model, so which I think is very surprising. And for axions, which is the thing that I said is maybe a little easier because you only need to get percent level sensitivity. We can even study it as a function of the phase transition parameters. And here you see, for different values of the temperature, we're seeing like what kinds of beta and alpha we would need to measure things to the percent level with LISA. And so anything below the curves could be probed. And I think it's possible to get alpha bigger than 1, but it's a little bit tricky. So I would really encourage you to cut this plot into around 1. But it's with LISA, if we want to get percent level accuracy, we would really need to get, temperatures that are very, very close to 10 to the 5 GeV. So, it would require some luck if we want to measure something like axions on LISA, but it's possible, which is, I think, already very surprising. And then if we have something more like the CIGO, which is, this more futuristic experiment, then over a wide range of temperatures, we can even reach, betas that are closer to 100, which is, a more generic prediction out of most models you would build. You could still get to this percent level precision. So I think getting to percent level measurements with futuristic gravitational wave experiments over a very wide range of temperatures is a very, very realistic assumption that we could, if we understand the foregrounds well, it's something I think we could really do. It means that we can measure it potentially we can measure free streaming particles better with gravitational waves than with CMB experiments. And again, also at a very different time in the universe. So even, even if we get to measure it with both, it's really important complementary information that we're going to get from this measurement. So with this, I just want to briefly tell you my conclusions and outlook. I hope I've convinced you that gravitational waves are an exciting new window into the early universe. There's lots of potentials for how much we can learn about early universe from gravitational waves, both whatever generated the gravitational waves, as I told you, is most likely coming from some DSM scenarios. So just the discovery of the stochastic signal would already be super exciting. But if we do measure something, then doing detailed study about the spectral information we get from that measurement can even encode information that goes beyond the thing that generated the gravitational wave and give us a new way to study cosmology in a way similar to what the CMB gave us when we started measuring the CMB with high precision. And as I said, we can measure different kinds of new radiation at very early stages of the universe. It's easier to detect it if it's free streaming. But it's, if the signal is sufficiently strong, we can even detect interacting radiation. And I think there's still lots of interesting ideas to pursue, related to trying to find imprints of DSM in gravitational wave signals, and something that we're actively playing around with. And hopefully we'll have more to tell you in the near future. Thank you.
Questions? I mean, I have a question, but it's maybe a little bit, off your topic. So you nicely explained at least the super horizon part, right? That there's this universality there, so you're leveraging that to make some observables. I mean, if I look at your models, there's also another falling part, which is the opposite regime where there's the very high frequency.
Mm-hmm.
Is there any kind of universality there? I mean, obviously the big signal region is right around the peak, but
yeah,
it's there for the high frequency that's controlling the fall off of the high frequency ones?
Not that I know of. I think that does vary more depending on what exactly you assume for the model. For example, I think that the like for, but I could be wrong. Like I could be remembering it wrong. But I think, for example, the power that you get from the bubble collisions versus the amount that you get from sound waves, I think predicts different slopes for that high frequency, for example.
Mhm.
So I think it's more sensitive to predict the exact microphysics of what's generating the anisotropic stress at high frequencies. But I could be wrong. That's my vague memory. I haven't looked into it in a while.
Maybe kind of related, more related to your talk. I mean, you talked about the super horizon modes, but you also alluded to the fact that you believe there's some universality that might go to somewhat higher frequencies, right? Because there's microscopic correlation lengths, the bubble size, or not microscopic, but less than Hubble, right?
Yeah.
And so, I mean, how do you want to comment on? You weren't totally resonatingly clear that that was universal with the same power. So can you talk more about that?
Yeah, it is. So I mean, it is universal, but you know, we have to assume that there is a separation, which, you know, that's the thing that's not universal. It's like we don't know what will be the separation between the correlation length and the horizon size. Yeah. But if we're free to assume that there is such a separation, then actually in all examples we've studied, for that regime the scaling would be exactly f cubed. So that regime is actually, you know, it doesn't get affected by the propagation effects that I've talked about. It doesn't get affected by the free streaming species. Doesn't get affected by the change in the equation of state. So actually, that's in some sense. I think that's not exactly how we've modeled things, but I think that, you know, if we wanted a smoking gun of this effect that we're talking about, this would be that we would measure, you know, f cubed scaling for some range of frequencies, and then we would see a break in that going in different directions that's sustained through lower frequencies. Because, you know, if we just measure the signal, we won't really know what meant to be super horizon or sub horizon. So I think, you know, the ideal case is that there is some separation between the correlation length and the horizon size, which allows you to get this f cube scaling for some, maybe like a decade of frequencies or slightly less. And then the change from f cube to something that's slightly different, I think would be, you know, the cleanest signal. But again, now I'm putting in some assumption that there's the separation of scales, which I don't know necessarily has to exist.
Okay. Other questions? Any questions from the Zoom verse? I don't know if there's anybody out there.
It's always the question, right?
Yeah. Any questions? Well, let's thank Gustavo, and we'll stick around a little bit if anybody wants to chat and ask questions without being recorded. Thank you very much.
Is it okay if I stop sharing so I